6.1 Entropy, a system property. Now we are going to look at the second law of thermodynamics from a quantitative perspective by introducing a new property called entropy. So entropy is a measure of the molecular disorder or a measure of irreversibilities of the system. It is an abstract concept. So energy is also an abstract concept. We are already familiar with energy. It is fairly easy to apply the energy conservation principles for a process. Entropy is not straightforward. Like mass and energy, entropy can be transferred across the system boundary, but entropy is not conserved. So entropy actually always increases for actual processes. So we'll get to learn how to set up the entropy balance equations. First, we will find out how to calculate the change in entropy. It starts from the Clausius inequality. So it states that for any cycle, the cyclic integral of delta Q divided by the temperature is always less than 0 for irreversible processes or equal to 0 for reversible processes. Consider a system at state 1 with specific volume V1. And the system goes through a process and ends at state 2. And the specific volume at state 2 is V2. So what is the change in specific volume during the process? It is simply the difference between the values at the final and the initial states. So delta V is V2 minus V1. From state 1 to state 2, there may be many different passes. But the change in specific volume is always the same for all processes. This is because the specific volume is a property. So it is not path dependent, but it is dependent on the state. A property is a point function. So it also applies to other properties such as pressure, temperature, internal energy, and enthalpy. So we don't need to know the path between the states to calculate the difference between the two states. Similarly, let's consider reversible cycles between the state 1 and state 2. So process A goes from state 1 to 2, and process B goes from state 2 to 1. So let's take a cyclic integral of delta Q over T between the two states. So it has two parts, integral from 1 to 2 and integral 2 to 1. The cyclic integral of delta Q over T equals 0. And this is because it consists of reversible processes. This is Clausius inequality. So integral from 1 to 2 equals negative integral 2 to 1. Integral from 1 to 2 through process A equals integral from 1 to 2 through process B. This concludes that the cyclic integral of delta Q over T is always the same for any internally reversible path between the two states 1 and 2. So it is independent of the path. It is a function of the end states only. Something must change between the two states. It has to be a property since it is only dependent on the end state. And this is what Clausius found. There exists a new thermodynamic variable at the states, and we call it entropy. denoted by S. So at state 1, entropy S1. At state 2, entropy S2. Entropy is a property. It is a property just like temperature, pressure, specific volumes, internal energy, and enthalpy. So delta Q over T depends on the end states only. It is a property. Let's say the differential property is ds. And that is equal to delta Q over temperature. So this is the definition of entropy. Or the change in entropy of a substance during a process is simply the difference between the entropy values at the final and initial state. So it is related to the heat transfer divided by the absolute temperature where the heat transfer occurs. So we must know the relation between the heat transfer and the temperature T to calculate the integration. So take a look at the equations. It is related to the heat transfer divided by the absolute temperature where the heat transfer occurs. We must know the relation between the heat transfer and temperature T to calculate the integration. Note that entropy change between the state 1 and 2 is same for all processes. It is independent of path. It is also independent whether the process is reversible or irreversible. Note that this relation is derived from internally reversible processes. But the result of it can be applied to any process, including reversible and irreversible processes. For example, the initial state is 1 and the final state is 2. It may undergo an irreversible process. But the entropy change between the two states is still the same, S2 minus S1. The capital S is the total entropy. So it is an extensive property. The lowercase s is the specific entropy. It is an intensive property. So what is the unit of entropy? So take a look at the equations. The unit of delta Q is kilojoule. And the unit of temperature is Kelvin. So unit of entropy is kilojoule per Kelvin. On a unit mass basis, so divide the equation by mass. Unit of specific entropy is kilojoule per kilogram Kelvin. And this is for specific entropy, and this is for total entropy.